here, Shane's out of town, I don't know.
He's on the road.
Oh,
He is on the
Yeah,
road.
he's on the way back though. So.
In time to be here for this?
Yep.
Oh, dang. Okay. So anyway, Brandon Perelman, who is a student in our Applied Cognitive Science program, as are most of you. Brandon is almost to the ABD point, right? You did your comps.
Yeah.
You've got to do your proposal.
Yes.
Which I think will happen this summer, hopefully. And then we'll be a dissertation bound. So he is going to talk to us today about investigating human behavior in route planning and search.
Thank you. Okay. So just to get into this, hi, by the way, good afternoon. We started looking at this problem from the point of view of pathfinding. And pathfinding refers to something that's really, really specific. So in terms of this entire problem space that comprises spatial problem solving, pathfinding refers to a whole body of research that in the basic science it's comparative psychology, and in the applied science you see some sports psychology investigating pathfinding, and actually our own Dr. Ward has a couple papers with David Eccles and studying orienteering pathfinding. And pathfinding refers to the body of research that's all about the agent's ability, so a person or a rat or a monkey, the agent's ability to localize itself in the environment, find things within the environment, and especially to learn the environment. And so a lot of the ways that it's studied is this neural network modeling where you have learning, like the Terminator did that thing where he tells John Connor, a neural net processor, a learning computer. So they learn the environment. And so that's the whole body of literature with pathfinding. Now the weird thing about that is that it's investigated from another side, which is the human factors point of view, and it's called wayfinding, and it's very similar, and there's no crosstalk whatsoever. These people never speak to one another. So the human factors community studies wayfinding, which is another type of spatial problem solving, but if pathfinding is all about the agent, then you could think of wayfinding as all about the environment. So the human factors professionals study something like, how can I improve the signage in an environment to make it more easily navigable and more understandable? And when you go to like an airport or a public transportation system or something like that, ideally it's supposed to be easy for you, if they have good human factors input, to navigate from one point to another. Now in addition to these two, you could think of pathfinding and wayfinding as sort of first-person forms of navigation, right? So you're either modeling a little rat moving throughout the environment, or you're modeling a person moving through a large public transportation system, but there's also this routing problem that's really similar to spatial problem solving. And that includes things like, if I'm going to route a bunch of mail delivery trucks, how can I optimally send those around to minimize my gas usage and stress on the trucks and stuff like that? So the whole body of literature concerning operations research and logistics would be concerned with routing problems. But it also includes some basic literature on problem solving, anything that could be broken down into Euclidean space. So we're talking about two-dimensional space, right? Flat, it could be three-dimensional, but presumably two-dimensional. And that's most commonly the traveling salesman problem, which we're going to beat like a dead horse. But it also includes things like the Tower of Hanoi, the Tower of London, where you have to transition through states to get to other states. You could think of that also like a Rubik's Cube, although a Rubik's Cube's kind of less so. Anyway, so these are just graphical depictions of some of the domains that we're interested in. So on the top there you see Chicago O'Hare, which if you're trying to escape Houghton, that's pretty much the only way out. But it also includes orienteering, which is sort of more of a sports approach. And here you see something like a routing problem. Now the difference between orienteering, so the pathfinding body of literature, and the wayfinding body of literature, and this routing literature, is that similar models accomplish both tasks, but the weird thing is that these are first person. This is accomplished using an overhead view. So it's sort of strange that one piece of cognitive machinery is involved in both of these. And the missing link there seems to be sequence completion. And a lot of these models that involve learning environments and understanding those really end up with, they'll present you with one part of the sequence and your brain completes the rest of the sequence. Some current event stuff include the stealthiest airplane in the world, this Malaysian airplane. So in a lot of applied settings, it's not just about navigating from one place to another. It's about finding things, right? So Shane and I traveled down this rabbit hole of investigating navigation for the longest time, and we're like, this doesn't explain everything, because in so many applied settings, there's more to it than that. And what that really is this strategic control where you're like, it's not so much about navigating optimally, it's about maybe I have another goal. Like maybe I need to find something. Or maybe my goals are really ill-specified and I'm on vacation and I just want to travel to the West Coast because the sunset's pretty there or something. It's not a discrete location, it could just be a region. And we started looking at wilderness search and rescue, which we thought was like a good applied domain. It originally started as an Air Force study, and wilderness search and rescue is, instead of finding people and blowing them up, you're finding people and saving them, so we thought that would be a more appropriate domain for a college and stuff like that. Help with IRB approval. But anyway, so wilderness search and rescue starts with a report of a missing person. So they say, my husband's lost and I haven't seen him for a while. And then they try to figure out, based on his experience, his age, his physical ability, and stuff like that, where he might be going and things like that. And the difference between this and a problem that you might see in the problem-solving literature, like a traveling salesman problem, is that it's not about plotting the overall shortest route through the environment. It's about finding the person as soon as possible. So it's a totally different strategy. So to introduce a traveling salesman problem, this is sort of the basis for a lot of the literature in spatial problem solving that we work with. We're only going to be talking about the Euclidean traveling salesman problem. There are others, so you could have it so that the cost of going between one city, one direction, so it could be asymmetrical, basically. But what this task requires you to do is you're given a map, not always of the United States, but some kind of a map, with a bunch of little points on it. And your goal is to connect them in the way that creates the shortest overall path. So you could start either wherever you want, or you're told where to start, or however the problem works. And you've got to sort of figure out what's the best way to do it. Now, this is called an NP-hard, or computationally intractable problem. And the reason for that is because in order to optimally solve this, like actually optimally solve this, you have to compute the path length associated with every possible permutation. So if there are 50 cities, you've got something like 50 minus 1 factorial divided by 2, some insane number of calculations that you would have to make. So it's computationally intractable for a large problem. Now, the weird thing about that, though, is somehow humans generate near-optimal solutions, and we believe that's through the use of heuristics. The most simple way that you can model this type of problem solving is with nearest neighbor models. And all that does is it says, I'm going to pick a city, then I'm going to look around. And I'm going to go, but the next city on my route, on my tour, is going to be the closest one to the one I was just in. So you're just going closest to closest until you solve them all. And the reason that it makes really crummy trajectories, well, aside from other reasons, is that you're going to get a lot of crossovers. And crossovers are necessarily inefficient. And so a lot of the algorithms that they come up with for solving these more optimally involve making and then breaking crossovers. When people try to come up with biologically plausible models of solving this, they come up with hierarchical models. And the idea there, and we're going to go through a few of those later, but the idea with hierarchical models is that they take a really difficult problem, a big difficult problem, and they chop it up into manageable pieces. And they believe, due to the structure of the machinery, the neural machinery, and the perceptual machinery involved, that that's a sensible approach, because those structures are themselves hierarchical. So to illustrate the problem that we have, anyway, in investigating this stuff, is that when you're faced with these decisions, it's not just a case, the same strategy doesn't apply in every case, I guess is the way you could put it. So, 2 examples, right? The first is, I don't know, a lot of you guys don't have kids, but imagine that you come home and you come home from the bar and you're like, oh, it's going to be a great idea, I'm going to play with this, this, and this, or whatever, you know what I mean? You're going to make food or something like that, right? And then you're too tired, so you go to sleep and you wake up in the morning and you're like, oh, what have I done? And all this stuff's on your floor, your kitchen table, or whatever. Well, solving that problem of how do I get all this stuff back into the drawers is sort of more like a traveling salesman problem than anything else. Because the cost associated with putting away, or rather the reward associated with putting away any of those individual items is the same as any of those other items. And the reason for that is that they all have to go away, unless you leave stuff on your counter like I did. So the rewards are fixed. Second of all, another characteristic of that problem is that you have to visit every location. You have to put everything away. So the optimal strategy for solving that kind of a problem, either the picking up the toys or the putting away the stuff on the counters, is to find the overall shortest path length that lets you do that, assuming you have enough space in your arms to carry it all at once. Now there's another type of task that you all are probably familiar with, and this is a bit optimistic, assuming that you drive a BMW. You might have a keychain or something, and you come home and you lose it, and you don't know where it is. And so if you're trying to find it, you're faced with a completely different problem than somebody who's solving this traveling salesman problem. It's still kind of a routing problem, it's still kind of a spatial problem solving kind of a problem, but it's different. And the reason for that is that once you find your keys, you're done. You don't have to visit every possible location. So I don't know how it is in your house, but at least in my house, there's like 3 places I'll put my keys. Either right by the door, which I should probably do every time, but I don't, on the desk by my computer, or on the kitchen table. And so I can sort of prioritize your mental simulation. When I'm looking for my keys, all right, well, I could check one of those locations. Those could be conceived of as the highest priority locations, right? Highest probability locations. But who knows what happened? I mean, maybe they fell off the desk. Maybe I took them to the bathroom for some reason, you know? They really could be anywhere, but I've got some assumptions about where I might find them. So in that case, you could think of your reward as dynamic. Now, why would you think of it that way? Well, in the traveling salesman problem, the reward is fixed because you have to visit every location. Think of it in terms of money. Time is money, right? And we all like money. So say you're making, I don't know, 20 bucks an hour. If it takes you an hour to find your keys, then that's 20 bucks you're missing out on, right? If it takes you 2 hours, that's 40 bucks you're missing out on. And if it takes you long enough, you might as well just go to the Beamer dealership and get another key fob because you've just wasted a ton of money. So we're trying to set up sort of a dichotomy between 2 different types of search tasks here. And in the latter task, your goal is to optimize or to minimize the estimated time to find. So in this case, you're trying to optimize for path length. In this case, you're trying to optimize for time to find. So in terms of modeling, this was going to be a modeling talk because, Shane and I model stuff. So our current capabilities or models are based on the hierarchical structure of both the human visual system and the human hippocampus. And we'll go through some of the individual models, but basically they assume that this problem is sort of solved from the bottom up, from a very perceptual system type, way. And it's structurally solved without a whole lot of input from strategy and top-down control. And it's not explicitly stated, but a lot of the basic psychology literature, modeling literature, is sort of comparative psych. So comparative psych, if you're familiar with it, is like we can understand humans by studying animals. And a lot of the way that these animal models work, they're primarily made for rodents and things like that, and so they're taking into account much different information than a human. Our theory is that those types of models would be insufficient for solving these types of problems because they don't include any kind of top-down control or any kind of strategy making that explains the other problem. So we can explain the traveling salesman problem type problem using these models fairly well. But what we can't explain is the general search problem. And if we want to apply these to applied tasks, so if we want to make this ecologically valid or rational, then we have to approach it from that sort of point of view. So some prior research that we have done. First, we modeled soldiers going through a shoot house, so I guess a house searching for contraband. And we also modeled participants in the lab and their performance in a wilderness search and rescue task using a simulated unmanned aerial vehicle. And the things that we noticed there were primarily that the simple model dynamics, so these are like the network activation dynamics and all the things that are fairly common to the rodent models, were sufficient to explain the local decisions that these agents were making. So these types of dynamics had no issues saying, if you're here and you want to go here, but there's a wall in the way, that activation through the network will explain how the person can get from point A to point B using hill climbing or something like that. But what it didn't explain, and what it required, was sort of a higher level plan that could drive those local decisions. So if you've got more than one room to visit, how do you prioritize amongst them? So the purpose of our present study was to test performance in these traveling salesman problem-like problems. So that's what we'll call this generalized search type strategy. And so what we did was we designed distributions of targets that we knew would totally trip up our models, totally mess with them. And what they would also do is force people to make one of two separate decisions. We also wanted to show that people could switch between two different types of strategies because it seems really obvious, but as of yet, nobody's really demonstrated that. Okay, so in order to force people or constrain them into these different types of strategies, we gave them two sort of vignettes. The first is that they were flying a taco copter. And this is a quad rotor UAV designed to deliver tacos. I think Amazon came up with something like this and then decided, I don't know if they were ever really going to implement it. It might have just been an April Fool's joke.
Somebody's delivering flowers now.
Really?
Yeah, flowers I read have been the only one that are allowed to do it so far, but it's a big deal questioning how many of these little guys are flying around the sky.
Right. And so one characteristic of this type of problem is that whether it's flowers or tacos or anything like that, the key is not who gets their taco first unless you're paying for some kind of prioritization. You want to plan out the shortest route because that would minimize fuel costs and it would minimize stress on the airframe and things like that. So we told them, look, you're Mr. Taco Copter. We want you to plan out a route to deliver tacos to all these different customers. In the second half of the study, we gave them the instructions that, okay, there's a child missing in the taco copter area of operations, and you're going to reroute the taco copter to search for a missing child. So now, instead of treating those customer locations as customers, you're now going to treat them as locations where you might expect to find this missing child. So this was the way we set up the two different strategies. The taco copter was meant to induce a sort of traditional traveling salesman problem type approach where they would try to minimize their path length. And the missing child vignette was supposed to set up a generalized search paradigm where they're trying to minimize the estimated time to find this kid. The hypotheses, these are formalized, but basically we expected that people would be able to switch between these two different strategies and produce different trajectories. So these were the distributions. We came up with these, and during the last presentation somebody asked, well, how did you guys come up with these? The truth is I just made them up. But we validated them mathematically. So if you look here, there's two ways that you could solve each of these problems. Two main ways. I mean, really there's millions of permutations that you could go through if you wanted to, but there's two main ways that you could solve each of these, and we're going to go through those in a second. The key point here is at the starting position, so where the participants start, taco copter base of operations, is the green circle, and the locations that they would have to visit are these blue circles here. And the map in the back you can disregard because I think all our participants did too. Okay, so if you wanted to optimize for path length, so you're starting here, and you have to visit all these locations. If you wanted to optimize for path length, where would you go first? Volunteer. Susie, volunteer.
From the green dot, where would I go?
Where would you go?
I'd hang a right. I'd go up to the line, the first closest one on the right, and then go right.
This one?
Yeah.
If you're trying to optimize for path length? Shortest path length.
Yeah.
Okay.
I would probably go to
That's
the
where I'd
end
go.
dot on the bottom and then basically go down that line on the bottom, go down to the bottom.
Where are you going first?
Bottom left.
There.
Yep, starting there, going across that bottom row.
Yeah.
No,
Okay.
no, you gotta hit that loop
Well,
at the bottom. You gotta make
Yeah, I was
that
gonna
loop.
go and hit the loop at the bottom, yeah.
Okay.
Yeah.
Okay. And if you were trying to optimize for estimated time to find, where would
Go
you
to the big
first?
group at the bottom first.
Sorry,
That's where you're
Susie.
gonna hit.
I'm sorry. Susie. All right, so
Well, that's what I said. I said the red way.
oh, okay. So
The red way is what I was trying to tell you.
okay. So the green line is the route that we would expect them to take if they're trying to optimize for path length. And what we did was we ran it every possible permutation. Sorry. We ran it every possible way and found the best way to do it. And if it wasn't right, like if it felt right but it wasn't mathematically right, we would play around with the starting location and stuff like that. So that's how we got these. The red line shows the way that you would go if you were trying to minimize estimated time to find. Because the goal there is you're trying to hit as many of these points as early in your search path as possible. Remember the whole analogy with defining the keys and you're making X amount of money per hour, so if it takes 2 hours, it takes 2x. Money is what's costing you to find your keys. That's basically what's going here. The longer it takes you to hit any of these targets, the less they're worth. So these are participants' performance when they were given the instructions to optimize for path length, so taco copter. And these were participants' performance when they were asked to find the missing child, so when they're optimizing for time to find. And what you would expect, according to our hypothesis, if people are capable of separating these two different strategies, you would expect that this would be completely green, and this would be completely red, barring a couple space cadets who did
Like
it their
myself.
own way.
I have a question. No, I have a
I didn't
question.
say that.
So, if I take and measure this green line,
Yes,
and then I measure this green line,
yes.
that doesn't equal this? Or does it come close to this?
So, in this, unlike a traditional traveling salesman problem, there's no requirement to return to base.
Oh,
That's the
get it.
difference.
Okay.
The participants were told that, you were not, I apologize.
See, that's where I would have done the red one thinking I have to come back anyway.
Totally, yeah, no, the instructions had said that when we put
Okay,
them on,
well,
I
there you go.
apologize. So what we would expect is that this would be all green and this would be all red. So this was the trial version, and we watched them do this to make sure that they understood. Obviously not closely enough. Okay, so in this case, if you were trying to optimize for path length, which way would you go? How would you do it?
For path length?
Yeah, the shortest path length.
You
Go
just
to the
pick-
right around the circle.
Yeah,
Yeah, you follow like a lasso, right?
Yeah.
yeah.
And if you were trying to optimize for time to find, how would you do? This one's not close enough.
All the bottom ones.
All the bottom ones, right. Yes, all the bottom ones. And you see people did that here too. If you guys want to keep going through these, how much? Yeah, keep playing this game. Okay, so in this way, this is pretty obvious. Which way would you go first if you were trying to optimize path length?
The singles.
Exactly, and if you're trying to minimize time to
Straight
find,
up to the group.
yeah. And you see people generally, we're getting like pretty good separation. Now I wish I could tell you this was like a huge sample size, but we're getting this type of separation with only 9 people.
Wow.
And we've run now like 16 or 17 more than that.
What is your access
Super
numbers meaning over here?
Proportion
Okay,
of participants
thank
who went that direction. I should label that, thank you. So in this one isn't so obvious either. Well, it's kind of a little bit obvious, but. So minimizing path length, which way would you go?
To
To the end of
towards
the
the
Z
corner.
and-
Oh, path length, yeah.
Path length, yeah,
Yeah.
exactly. And so if you were trying to minimize time to find, you might just
Probably,
go straight for the,
Yeah.
or go
Closest.
for the corner, because
go for
the
the
or
corner.
go for the corner. Well,
Because
it's funny
there's
you would
a
say
tight
that.
grouping.
It's funny you would say that. So we actually made a distribution that, in case this wasn't strong enough to produce the kind of effects we would expect, which in fact it wasn't, because some people said, you know, I still think that having to fly this hypotenuse of this
Yeah.
triangle is so long that maybe it's not worth it.
Mhm.
And so what we see is people sort of saying, all right, I get what you're doing, but I'm still going to fly it my way. And you see how that separation sort of increases. So this is like total strategy control type stuff going on here. We get really good separation. Oh, this one's kind of weird.
Mhm.
I already showed you, so. Anyway, so these are the two different ways that you might solve these. And of course there were some people who did completely crazy things, but they were definitely the minority. So in terms of our behavioral results, the first two things pretty much say the same thing. So not only was instruction alone sufficient to change their trajectories completely, but it changed them in a way that created, that was optimal, right? So people were using whatever kind of heuristic, they were applying this not only to a traveling salesman problem type problem, but also to a problem where you have to minimize the time to find. So we believe that hardwired perceptual mechanisms are insufficient, and we're going to go through some modeling stuff to hopefully convince you of that as well. Okay, so prior research in modeling the traveling salesman problem itself. And this is just the Euclidean, two-dimensional optimal path length type traveling salesman problem. There are a bunch of different ways that you can model this. You could solve it using a nearest neighbor approach, which is strictly local decisions. So we went through that before. It's like, if you've got a point here, 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 and here, and you start here, the nearest neighbor is this guy. So you go over here. Then you say, all right, how far is this? How far is this? How far is this? Whichever one's shortest, which I imagine is this one. And so this would be 1, 2, and then it would be this one, and then this one. So you can imagine that in some problems, that might solve it optimally, but in other problems, it absolutely wouldn't. So to address that, the Vickers model uses a hierarchical approach to that, which it's a lot easier to see it, and we've got some graphics here that really clear it up. Zygmunt Pislow, who was the coolest name in the world, has a cluster model called the foveating pyramid model. And this is based on the structure of the visual system. What it does is it basically takes the entire search space and cuts it in half by the number of cities or targets or whatever in each half. And it keeps cutting that, clustering off targets and dividing them into clusters. And the idea there is that it's based on the hierarchical structure of the visual system. There's also a region model, and that's the Ten Brink and Weiner model. And their model, rather than dividing it by clusters, it divides the environment by rough geographic region. And they've applied that to things like vacation planning and other very applied type fixations. And they have pretty neat ways of testing that. And finally, McGregor came up with something called a convex hull model, which we find is pretty effective. And what that basically is it says that people tend to do, if you've got a square area, like a traveling salesman problem in a very squared type, basic science area, then you have to return to the place where you started. So people are going to do a huge loop-de-loop. And we know that that holds even in cases where people don't have to return to base, just from plotting behavioral data and having people solve similar problems. So it sort of makes sense. But the idea there is that in all of these models, you've got some sort of a higher level plan. Now the question is, what's driving that higher level plan? And in this case, in all of these cases, the same machinery that's driving the higher level plan is driving the lower level plan. What we would argue is that that higher level plan is completely malleable and subject to top-down control completely. So what does a model need to do if it's going to address all of these tasks? We've got, mental simulation and walking through an environment, so we've got pathfinding. We're not going to worry about wayfinding. And we're going to worry, routing problems we have to solve too. So we know that solving these types of problems, these computationally intractable problems, requires some kind of heuristic whereby you break up the problem into little pieces, and then it's a lot easier to solve a bunch of little problems than it is to solve this 50-city, 5 bazillion possible solutions type problem. We also know that it should be constrained by biology. So, you should be able to look ahead and plan ahead your moves a little bit, but you shouldn't be able to plan ahead for, a 50-city problem or something like that. So it should be constrained by the constraints of working memory, visual system, and things like that. We also know that local decisions should be relatively inexpensive. So a lot of these models, like the foveating pyramid model, it breaks it down until you can solve the problem exhaustively. But if I was to ask you to plot the trajectory that you would take through that environment, I know that you wouldn't start at every single location and calculate every permutation imaginable. So it's sort of a shortcut, and we'd like to avoid that if possible. We also know that in terms of intelligence, it should be able to weigh distance versus reward, and that's about it. Because a lot of these things, a lot of these dynamics, like spreading activation and nearest neighbor, are driven almost entirely by distance to first contact. So it's going to do it, but it's not going to do it well. Our global decisions should be, like we said before, malleable. So it shouldn't depend on the exact same type of machinery. So we've got two types of models. The first is a model that does exactly what I just said it shouldn't do. It uses the same dynamics to solve the problem at multiple levels. So this is our lasso thing that we talked about before, that target distribution. And you see it over here in terms of the actual implementation of it, and over here is sort of like the brain, the planning of it. And the starting location's in red, and it's that little circle over there. And what this does is it basically says, I'm going to place a number of disks. And these are represented as disks, but what they actually are Gaussians. And I'm going to say, I'm going to break the problem up into a number of different pieces. And we tried to make this consistent with the number of pieces involved in phase precession, which if you guys are like into navigation literature and stuff like that, it has to do with working memory and stuff. Anyway, so we had it place these disks throughout the environment and then jiggle them and move them around and see how we could get the shortest path through the disks. And then we made it so that the agent itself would only solve for the points that belong to each of those disks in sequence. So what it does is it solves through spreading activation this problem, which is a 4-city traveling salesman problem. Think of it that way, right? It's got to go from here to here to here to here to here, right? And then within each of those, it says, all right, I'm going to solve this first, so I'm going to solve this problem exhaustively. Once that's done, I'm going to go to all the points belonging to this Gaussian, I'm going to solve them. And then it's going to go here. Does that make sense?
You're going to go to the city, and then you're going to go to the houses in the city.
Yes, yes. And so we expected that this model would behave a lot like the cluster models, because what it's doing is it's saying, I'm going to use one basic set of neural machinery to solve this problem at 2 different levels. A lot of the cluster models solve it at, you know, however, whatever numbers in a whole ton of levels. We're only using 2. And the trajectories that we got are like this. So I just wanted to show this to you guys, not because I think it's actually solving it in the way that humans do when they're using a general search strategy, but just that it sort of behaves that way, and we believe that's a product of the target distributions, not of... So I'll show you the good news, and then I'll show you the bad news once I get your hopes up. Okay, so on the right here is a human trajectory when they're solving the general search task for this distribution. This is when they're solving it as a traveling salesman problem, and this is the model's trajectory. So you see it's kind of behaving like a general search trajectory. It's solving all these guys down here, then it's going up here, solving these, etc. That one's a little ugly, but you get the idea. Very similar, right? This one's kind of a mess too, but you know, it's similar in that it's not trying to take into account the entire path. It's trying to optimize for, I'm going to hit this as soon as possible, and then go from there. You know, here's a problem. When you give it a real traveling salesman problem, it fails absolutely miserably. And part of the reason for that is that it doesn't take into account where it's going in relation to where it's been. And I tried to incorporate some dynamics for that. So I tried to weight the spreading activations, basically like if you were to throw a rock into a pond, the activation's strongest in the middle and then diffuses outward. I tried to make it so that it would weight it sort of directionally, and that didn't work at all, because it's still driven almost primarily by distance of first contact. So what it does is it produces a whole ton of crossovers. So it has no problem solving this problem, this, and this. In terms of the large macro plan, the issue is that when it gets down to the nitty-gritty, it finishes this, and it's like, well, where do I go now? It's not very intelligent, if that makes sense. And it's not the way that humans are solving it, because a human is like, well, if I get to this guy, I gotta hit these like almost first, because I know I have to go here next. So the one set of machinery just isn't appropriate for solving these types of problems. So I wouldn't say that it optimizes for shortest, lowest time to find, but I will say that it definitely doesn't optimize for shortest path. So it's not that it's a good model in terms of a general search strategy, it's just a really bad model in terms of a traditional traveling salesman problem approach. But it looks like a good model for search strategy because it's of the way the distributions are laid out. So our current modeling effort is like this. And this looks like a total mess, but I promise you it'll make sense when we explain it. Okay, so this is our traveling salesman problem. Bunch of different cities all hanging out together in clusters. This does something sort of like a convex hull, but not really. What it does is it says, I'm going to make a plan that's really approximate. So in this case, the red triangles and lines, that's the higher level plan. And what it's saying is, I'm going to start, well, I necessarily have to start here, but I'm basically just going to cover this entire space, right? And as you see, the plan that it comes up with is totally crazy. there are a couple limitations of it, which we'll go into later, but the gist of it is that it creates a bunch of line segments and then solves along that line segment. So if this is your current, if you've got cities here, 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 and here, and your line segment is like this, what it does is it says, all right, I'm going to make a value for each of these. Your distance along the line, and then your perpendicular distance to that line, and that's sort of the distance, and what it does is it sorts these, say this is like 1, and this is like 1.2, and this is like 4, and this is like 3 or something. These are totally arbitrary values. It just says, I'm going to solve these in ascending order. So what it's doing is it's creating a linear plan where your brain is saying, I need to go from here to here, and here's how I'm going to do it.
So kind of it takes a line of best fit approach and then hits them in the order that they're following.
Well,
On
this
that
is
line.
actually a line of completely arbitrary fit, but we're going to make it a line of best fit
Right, that's what,
by iterating through it a million times. So this process doesn't represent anything biologically relevant whatsoever. This is sort of our like black box where we're not sure what's going on yet, but what it does is it iteratively creates 200 different plans. You could make that whatever number you want. These are just all the different possible plans laid over on top of one another. And it basically just says, I'm gonna run it the way that I ran it before, and I'm going to calculate the total path length. So I'm going to calculate the length of this black line. And if the new path length is less than the old path length, then I'm happy with it. If not, we're going to throw it out. And it does that 200 times, and it comes up with something like this. Now, optimally, the model would allow for insertions and deletions. So right now, this plan always has 9 legs to it. But there's no reason to think that a plan should have to have 9 legs to it. Because in orienteering, it could have like 25 or 50, or I think that's like a common number. Anyway, so we'd like to have it so that it would minimize the complexity of the larger plan, and we'll get to that later. But this is just sort of a quick and dirty way of showing what this type of model can do. And for the most part, it solves it almost optimally. I mean, there's a couple cases here where clearly it's not very good. Like, over here, obviously, it should hit that first. And a lot of that has to do with the fact that these line representations, they're not actually segments. The way that they're programmed, they're actual lines. So, like, if there was a point all the way over here, it wouldn't belong to this segment. It would belong to this segment because this just extends sort of crazy.